Good day everyone. I am here today again for another lecture, and this time around I'll be talking on momentum and impulse, and then simple harmonic motion. These are the two things I'll be discussing today on. So I remain myself, Dr. IBRAHIM INUSA, for Physics 111 class. Momentum and impulse is are the two things we'll be discussing, after which I'll proceed to simple harmonic motion. Momentum, as the saying goes, is the product of the mass of a body or object and its velocity. And this momentum is measured in kilogram meter per second squared and is denoted by the symbol P. For an object to have momentum, certainly that object must be moving, and what that means is that the body has to be in motion, because without motion there can be no velocity. So for any moving body, there is velocity, and hence that body is bound to have a momentum, because every body or object has mass. But if a body is static or is in one position without any movement, there will be no velocity. That body will not have velocity. But once the body is set to motion, then it will now have a velocity. And what this simply means is that without velocity, there will be no momentum. But every object we know has mass. But if that body is not moving, then there won't be momentum. So momentum, we can here say that depends majorly on velocity. Since without velocity there will be no momentum. So as I earlier put it, momentum is the product of mass and velocity of any body or object. Momentum is mathematically given by the expression P is equal to mass times velocity, because we know that product simply means multiplication. So momentum is mass multiplied by velocity, and as we all know, mass is denoted by m and velocity is denoted by v. So momentum is simply put P is equal to mv. All right. Momentum is a vector quantity. Why? Because it has both magnitude and direction. Since it's dependent on velocity, and velocity is a vector quantity, and so momentum is also a vector quantity. And as we all know, that vector is any physical quantity that has both magnitude and direction. From Newton's first equation of motion, which is given as v equal to u plus at, where v is the final velocity, u is the initial velocity, a is the acceleration, and t is the time, we have that v is equal to at, and that happens when u is 0. U equal to 0 simply means that the initial velocity is 0, and so if we now substitute 0 for u in v equal to u plus at, we are now going to have v equal to at. Therefore, P is equal to MAT. P is equal to MAT because the V now has been substituted by AT, because I just said that from Newton's first equation of motion, V equal to U plus AT, and then we said if the initial velocity is 0, V will now be equal to AT. So we are now replacing the V with AT, and so our momentum is now P equal to MAT. And again, MA is known to be force. Force is simply MAT. So again, if we now substitute MA by F, then we will now be having P is equal to Ft, where F is the force and T is time. The product Ft is referred to as the impulse I, which is defined as the sudden application of a force to an object. So if an object is either moving or is an object is moving, and then there is a sudden application of a force, then that object is bound to have impulse. An impulse, as I earlier said, is simply the product of force times time. Impulse is measured in Newton seconds because, as you can see from the definition, it is simply force times time, and force is in Newton, time is in seconds. So the unit of impulse is Newton seconds, that is NS. We have worked examples on this, and one of it is a resultant force is 100 Newton acts on an object of mass 10 kg in 10 seconds. Calculate the impulse of the force. What is the impulse of the force? If a force of 100 Newton acts on an object of mass 10 kg in 10 seconds, we simply have that F from the question now, we have that F is 100 Newton, mass is 10 kg, and T, that is the time, is 10 seconds. And momentum is simply given by I is equal to Ft. So all we need to do now is to substitute the values. And the values here are that F is 100. We write the 100 in place of F. Now times T, which is 10 seconds, in place of T. So we now have that 100 times 10 is going to give us 1000 seconds. All right, that is that. In the problem, you can see 100 Newton, which is force, mass 10 kg, and time 10 seconds. But if you look at what we have solved, in the expression for I equal to Ft, there is no mass. And since there is no mass, we are not going to make use of the 10 kg. But assuming if we use the other expression by replacing F with MA, then we are going to have make use of the 10 kg. But in this case, acceleration will not be there, and so the problem will still not be solved. So in solving problems, you look at the physical quantities that are given in that problem, and then you bring out the expressions for that quantity that you are asked to find or to calculate. Then when if that quantity has more than one form expression or formula, then you look at the one that will suit the problem you have at hand. If you look at all the given physical quantities in the problem, or the data that are given in that problem, and then you look at the 2 or 3 expressions for that particular quantity you are asked to find, then look at the one that you think will best match, and then you make your substitution, and you get your final answer. So in this case, the impulse is simply 1000 Newton seconds. Example 2 says what change in velocity would be produced on a mass of 8 kg if a force of 30 Newton is made to act on it for 15 seconds. I come again. What change in velocity would be produced on a mass 8 kg if a force of 30 Newton is made to act on it for 15 seconds? The solution goes this way. First of all, bring out all the things that are given in the problem, in the question, and we have that mass is given as 8 kg, F is given as 30 Newton, and T is given as 15 seconds. So we all know that Ft is equal to mv, which is what? Momentum. Ft is equal to mv, which is what? Momentum. And this implies that 30 times 15 is equal to 8v. In this case, we have substituted the values that are given in the question, where F is 30 Newton, 30 is there, multiplied by the T, which is 15 seconds, and then equal to, on the right hand side, we have M, which is given as 8, so we have 8 now, multiplied by V, and the V in this case is what is not given in the problem, and that is what the question says we should find or calculate, because the question says what change in velocity would be produced. So we are to find a change in velocity that is produced when all this happens. So if we do the mathematics here now, we have 30 times 15 equal to 8v. All we need to do is this: to find v, we make v the subject of the formula or the expression, and that will give us 30 times 15 divided by 8. If we do the mathematics, the final result is 56.25 meter per seconds. That is the change in velocity that would be produced on a mass of 8 kg if a force of 30 Newton is made to act on it for 15 seconds. So these are the 2 worked examples on momentum and impulse, and I think this is where I will say we have come to the end of momentum and impulse. So the next thing we'll be talking about now is simple harmonic motion. Simple harmonic motion is any motion where a restoring force is applied proportional to the displacement and in the opposite direction of the displacement. In other words, the more you pull it away, the more it wants to return to the middle. What this simply means is that simple harmonic motion is, simply put in a layman's language, a to and fro kind of motion. A motion that has to go and come, go and come. When something is to and fro, it means it goes to and forth, back and forth. I mean, it will go forward, come back, go forward, come back, and then at a point it will come to a standstill. And that point of standstill is the equilibrium point. We call that point equilibrium position. So simply we are saying that simple harmonic motion is a to and fro motion of a body or an object. And examples of such to and fro motions are if you have a, say, pendulum bob tied to a spring or a rope, and then you hang it either on the ceiling or you are holding it in your hand facing downwards, and then you try to displace it a bit just to a small angle. You will see it going and coming, going and coming. At first it will be at the center. When you display it to the, say, to the right, and then you release it, it will come back to the center, pass the center, go towards the left, stop somewhere, come back to the center, go to the right, and the motion will continue like that, to and fro, to and fro, to and fro, until it comes to a stop again. So a basic example of this is a mass on a spring, because the more the mass stretches the spring, the more it feels a tug back towards the middle. If you have a string, for instance, and then you hook it to a static object, and then you pull it, of course it will extend, and as you are pulling it, it will be forcing itself to go back to its original position. As soon as you release it, what happens? It will go, it will be dangling like that until it goes back to its original position. Those are examples of simple harmonic motion. A mass on a spring can be vertical, in which case gravity is involved, or horizontal on a smooth tabletop. It can be horizontal on a smooth tabletop. It can be vertical, just like the simple harmonic motion. But whichever. The thing is, whether vertical or horizontal, if you pull it, it will force it, it will want to go back to its original stable position. If you imagine pulling a mass on a spring, then letting go, it will bounce back and forth around an equilibrium position in the middle. Like with all simple harmonic motion, the velocity will be greatest in the middle, whereas the restoring force and therefore acceleration will be greatest at the outside edges, at the maximum displacement. Another example of simple harmonic motion is a pendulum, just like I earlier said, though only if it swings at small angles. You have a pendulum, yes. You have a pendulum bob tied to a rope, yes, agreed. But if you are just holding it facing the ground, the bob is facing the ground, and then you are holding it in a stable position without making any displacement of the bob, of course there will be no motion, and there will be no simple harmonic motion. But once you displace it to a small angle, just a small angle, and then you release, then we'll now have a motion called simple harmonic motion. All right, so we can see an example of a spring hanged to one side of a table, and that is why you can see it is horizontal, and then a mass is hung on one end while the other hand is hooked to a stable object, and then the mass is now pulled away from the original position of the spring, and you can see that the equilibrium position is where we have x equal to 0. When x is 0, then it is now pulled towards the right hand side. From this diagram, as you can see, it's pulled towards the right hand side, and then as it's being pulled towards the right, you can see an arrow going back towards the center where x is equal to 0. The arrow is going back there. Why? Telling us that as you are pulling it away from its stable position, it is tending to go back to its stable position. So, and in the second diagram, you can see that it was still at the equilibrium position. It is not moved, and so at that point, Fs is 0, that is F is 0, and then A is 0. Because since it's not moving, there will be no force. That means no force is applied. That is why it is 0, and no acceleration is obtained, and that is why it's also 0. Then the third diagram is saying that x is equal to negative a. When x is equal to negative a, what happens? The spring is kind of pressed. You know, the equilibrium position is the second diagram. Now the first diagram, it was moved, extended to the right, and it forced itself back to the equilibrium position. Now the spring is a kind of pressed, forced to go against itself. And what happens? At that point, x is negative a, and also F is there because that it is the application of the force that forces it to compress. In this case, it's not extending, but it is compressing, and that as it's compressing, it will also want to force itself to go back to the original position. So whichever way you do with a spring, whether you are pulling it or you are pushing it, all it wants is to go back with its original position. So when after the push has been released, what happens? It has again come back to the original position. So you can see that the first diagram is saying x equal to a, where it is pulled to the right hand side, and with the application of a force, and that force is now a pull force. In the second diagram, it has come back to its original position. In the third diagram, a push force is applied to it, and it forces it to compress towards the left hand side, and at that point our x is equal to minus a. The fourth diagram is when the pull force has been released, the push force has been released, and the spring has come back to its original position again. And the last diagram, which is the fifth one, is just a repeat of the first diagram. So this is just an example of a spring mass system oscillating through one cycle about a central equilibrium position. So when this kind of motion is taking place, of course, when you release it, it will not just go there and stop like that. It will continue to go and come like that, to and fro, until it gets stopped at the equilibrium position. So that process of going and coming, to and fro, is what we refer to as the simple harmonic motion. And we have what we call when you pull, in the case of this spring now, as you pull it away and you release it, it will go back to equilibrium, and then it will come back again. That is when you can now say you have a one complete cycle or one complete oscillation. But once you release it and it goes, you cannot count it as one complete oscillation. It has to go and come. That is where you can say you have one complete cycle or oscillation. Then examples of simple harmonic motion. One is motion of a mass suspended from a spring. That's just what I have explained. But then in this case, it is not horizontal as in the case we just explained. That one is horizontal. But in this first example now, it is vertical. The spring is suspended on something, and then the mass is attached to it at the other end. That way, it is vertical. Two, we have beating of the heart. Beating of the heart is something that repeats itself after equal interval of time. And this simple harmonic motion is simply also the type of motion that repeats itself after equal interval of time. It's a repeated kind of motion, and the repeat is such that it is always after equal interval of time. that repeat will take place. And so heartbeat is, beating of the heart has a motion which is simple harmonic in nature. Then 3, we have motion of a piston in a gasoline engine. We have a piston in either motorcycle or car engines, and those pistons, their motion is vertical. It goes and comes, vertical in nature, goes and comes. If you have a case to visit a motorcycle mechanic and then ask him to open, maybe if you meet him at the point that he's opening what we call plug engine, when he opens the top cylinder, what you will see is a cycle, is one opening that has a kind of tin of milk shape of another iron that is inside that opening. That shape that looks like the tin of milk is what we call the piston, and it is inserted into an opening. And so the motion is, it comes out, it goes in, it comes out, it goes in a vertical form. That is a piston, and that going and coming in vertical form is what we call a simple harmonic motion. And that is why the motion of a piston has to come in under simple harmonic motion as an example. Okay. Then another one is motion of a loaded test tube in a liquid. When you load a test tube, for those of us that have the opportunity to do chemistry practicals, then you load the test tube and then you release it into, you put it in a liquid. What happens? It goes in and comes out of the liquid, and the going in and coming out is repeated after an equal interval of time. That's what happens when you have a loaded test tube and you try to put it inside the liquid and try to kind of force it inside the liquid a bit and release. It will be going and coming in and out like that until it will also finally stop. All right. So under simple harmonic motion, again, we have what we call speed and acceleration of simple harmonic motion. Speed, of course, we already know what speed is. Speed, we say, is distance over time. And then in this case, speed of a simple harmonic motion is given by the expression V is equal to omega r. The r in this case is a lowercase r, and then it is also given as omega a. R is simply radius, but in this case the radius is the amplitude of the motion, and so r is the same thing as a in this case. This means that the linear speed equals the product of the angular speed and the radius or amplitude of the motion. So radius and amplitude are treated the same in this case, and simply the linear speed is the v, and we said is equal to the product, that is multiplication of angular speed, which is omega, and the radius or amplitude, which is the r or the a. So this is simply what we mean by speed of simple harmonic motion. Then acceleration of simple harmonic motion. The acceleration, as we all know, is simply what? What is acceleration? Is simply velocity, isn't it? And then divide by time. Velocity divided by time is simply, or change in velocity divided by time is simply acceleration. And in this case of simple harmonic motion, we say acceleration of a simple harmonic motion is given by A is equal to minus omega squared x. Minus omega squared x. And that minus, the negative sign there, has implication. And the implication is that it indicates that the acceleration is directed towards the center of motion, while the displacement is measured from the center outwards. That is the implication of that negative sign there. It's not just there, it's there to tell you something. The negative sign indicates that the acceleration is directed towards the center of motion, while displacement is measured from the center outwards. That is the interpretation of that negative sign that you are seeing attached to that expression. Again, under simple harmonic motion, we have period, we have frequency, and we have amplitude of simple harmonic motion. The period of simple harmonic motion is the total time it takes for one complete cycle of motion of a vibrating or oscillating body. For you to have one complete cycle or one complete oscillation, then the total time it takes for that to happen is what we refer to it as period. So simply put, period is the total time taken for one complete oscillation or cycle. The total time taken for one complete oscillation or cycle is what we mean by period of a simple harmonic motion. It is measured in seconds and given by the mathematical expression T equal to 1 over F equal to T over N. The T of period is the uppercase T, that is the capital letter T, while the T over N, this small or lowercase t, is the time. It is the time. It is the time for, let's say, not a particular number of oscillation. The time it takes for a particular number of oscillations. Assuming you have 20 oscillations, and then you set an object to a simple harmonic motion, and then you allow it to do 20 oscillations. After 20 oscillations or cycles, you start the time, and then you set the something. You set the motion, and then the time is reading as the oscillation is taking place. You start counting 1, 2, up to 20. As we are saying 20, you are stopping the time. Whatever it gives you is the time taken for 20 oscillations. So for you to get the time for one complete oscillation, you now have to divide that time by the number of oscillation. That is why we now have capital T is equal to T over N. T is the time taken for a particular number of oscillation, while N is the number of oscillations. The next is frequency of simple harmonic motion. Frequency is the number of complete revolutions or oscillations. You keep seeing new terms coming up. Revolution, oscillation, all mean the same thing. So frequency is the number of complete oscillations or revolutions in 1 second made by a vibrating or oscillating object or body. It is measured in hertz and given by the mathematical expression F is equal to 1 over T, which is equal to N over T. Remember, period with T we say is 1 over F and is T over N, and frequency is simply the inverse of the period, and so the reverse is now the case. F is now equal to 1 over T, and then in the other case it was T over N. In this case it is N over T, because it is the inverse of this now that has taken place. So T and F, when you change their positions, you get period and frequency. And again, we have amplitude of simple harmonic motion. Amplitude is simply the maximum displacement of a body performing simple harmonic motion from its central point or its equilibrium position. That is what we refer to as amplitude, and it is simply denoted by capital letter or uppercase A. That is amplitude. Then the simple pendulum. A simple pendulum has a small diameter bulb, like I explained earlier, and a string that has a very small mass but is strong enough not to stretch appreciably. The linear displacement from equilibrium is S. The length of the arc Also shown are the forces on the bulb, which result in a net force of mg sine theta towards the equilibrium position. That is a restoring force. So this, like I explained earlier, a simple pendulum is simply a bulb tied to either a rope or a string and then hanged either on a ceiling, on a retort stand, or you are holding it in your hand high up. That is simply a simple pendulum. So you can see this diagram is simply an illustration of simple pendulum. You can see the red dotted line is hanged. The black horizontal line is simply taken as the ceiling, and then the red dotted line is simply the rope or the string, and then the blue ball by the right hand side with 3 arrows pointing to different directions is simply the bulb. So it can be seen that the dotted line is the equilibrium position of the simple pendulum, but then it has been displaced a bit to the right, just small displacement. It has been displaced a bit through a small angle given as theta to the right, and then at that point, if it is released, it will come back to this dotted line and then extend the movement to the left hand side to equal angle as the theta by the right, and then at that point you stop, come back again to the equilibrium and go back again to this position you are seeing at your right hand side, go back to the left, come back to the right, go like that continuously. And every movement as it is at the left hand side, right hand side now, if it is released to come back to equilibrium position, it will extend to the others, to the left hand side, come back to the right hand side where it is. That is where you can now say you have a complete oscillation. So one complete oscillation is simply at the point you display it and you are holding it. Once you release it, it has to go past the equilibrium to the other side and then come back to the point where you released it. That is where you can now say you have one cycle or revolution or oscillation. All right. Now, the length from the ceiling to where the bulb is attached on the rope or the string is what we call L, or length of the pendulum, and is given by capital L. And then we have capital T. There is the time for one complete oscillation, and then the M is simply the mass of the bulb. Okay, then the weight of the bulb is the arrow, the red arrow pointing downwards, and it is given there as W equal to mg. All right, then the small displacement is given by S, which is the displacement of the bulb from its original position. Then we also have that mg sine, we also have mg sine theta. So this is an illustration showing a simple pendulum and its kind of motion, which is simply referred to as simple harmonic motion. Pendulums, we can say, are in common usage. People are using pendulums. Some have crucial uses. Some have crucial uses, such as in clocks. There are clocks, wall clocks, that have this pendulum on them, that it swings. Some are for fun, such as the child's swing. If you go to nursery schools or kindergarten these days, you will see children sitting on string, and then one person will push the person away, and then the person will come back and then be going like that, and the children will be happy, and they are playing that kind of play, of which they may not know what it is, but that motion they are exhibiting is simply the simple harmonic motion. And some are just there, such as the sinker in a fishing line. That sinker in a fishing line is simply also exhibiting a pendulum. For small displacements, a pendulum is a simple harmonic oscillator. A simple pendulum is defined to have an object that has a small mass, also known as the pendulum bulb, BOB, which is suspended from a light wire or string. Exploring the pendulum a bit further, we can discover the conditions under which it performs simple harmonic motion, and we can derive an interesting expression for its period. That is the total time for one complete oscillation. We begin by defining the displacement to be the arc length, just like we have seen in that diagram, that illustration, where we have S as an arc length, and that we say is a displacement. We see that the net force on the bulb is tangent to the arc and equals minus mg sine theta. The weight mgh, has components mg cos theta along, has components, sorry, the weight mg has, not mgh as I said earlier, the weight mg has components mg cos theta along the string and mg sine theta tangent to the arc. Tension in the string exactly cancels the component mg cos theta parallel to the string. This leaves a net restoring force back towards the equilibrium position at theta equal to 0, because at equilibrium there is no displacement, so the theta there is 0, because theta is the angle, and so when there is no angle, theta becomes 0. So I think I can say we have come to the end of this class. So I wish you good luck